Scientists debate a range of ideas about how life on Earth began. The most widely accepted scenarios involve the geochemistry of the planet's surface. In the early universe, vast molecular clouds of dust and gas condensed to form a protostar, surrounded by a protoplanetary disk. Tiny dust grains, consisting of silicate minerals coated with ice, stuck together and assembled into larger particles. Earth was formed. Because it was not too hot and not too cold, not too dry and not too wet, liquid water existed on the surface. The first land was probably volcanic, forming island arcs in a vast ocean. Ponds or lakes in volcanic regions were likely environments for jump-starting life. The early atmosphere had no oxygen. It consisted mainly of nitrogen and carbon dioxide, with smaller amounts of hydrogen, water and methane. Lightning, asteroid impacts and ultraviolet light from the sun acted on the atmosphere to generate hydrogen-cyanide, a compound of hydrogen, carbon and nitrogen. Raining into volcanic or crater lakes, the cyanide reacted with iron brought up by water circulating through rocks. The resulting iron-cyanide compounds accumulated over time, building up into a concentrated stew of reactive chemicals. Life as we know it requires RNA. Some scientists believe that RNA emerged directly from these reactive chemicals, nudged along by dynamic forces in the environment. Nucleotides, the building blocks of RNA, eventually formed, then joined together to make strands of RNA. Some stages in this process are still not well understood. Once RNA was made, some strands of it became enclosed within tiny vesicles formed by the spontaneous assembly of fatty acids lipids into membranes, creating the first protocells. As the membranes incorporated more fatty acids, they grew and divided. At the same time, internal chemical reactions drove replication of the encapsulated RNA.